Hello, chat. Hello. Screen. Welcome on in. So, I finish next week, next Friday, which is feels crazy to think about. Honestly, I have my last exam on. I have my last exam on Friday, and then I'm done with A levels. Unless I fail one and I have to repeat them, but I doubt that would happen. Honestly, um, yeah, I still haven't gotten my chemistry folder out, so and the stuff I wanna revise from and kind of talk through. But yeah, I have 3 more exams left. Then I am done. I think I said this, I mentioned this last stream, but I'm thinking that after like, the week after I finish A levels, so that would be, not next week, but like the week after. So week beginning the 26th. I want to do a all week stream. So I stream Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And I'm kind of dying with this cough. But yeah. So my next exam is paper 2 for chemistry, which is on organics. So let me get up. I haven't decided what topic I want to go through yet. So I'm just gonna go through some of my like organic like booklets and see which one I want to go through. I could theoretically go through organic synthesis, but I've been through organic synthesis quite a bit. Okay, so I also cannot remember if I said I wanted to go through anything else. Did I want to go through? Okay, I haven't been through chromatography, so I think I wanted to go through chromatography, and if we have time, I'll go through acids and bases and buffers. Because this is quite a thin, like, booklet. But then again, acids, bases, and buffers, it's like quite a decently sized, like, topic. So, unless I just go through indicators, that's like, which is like within the acids, bases, and buffers, like, topic, and where did I put this one? So, yeah, if we get through chromatography and qualitative analysis, we'll go through indicators. I think I want to put my fan on just so I don't get too hot. Yeah, that is white screen. Okay, so last week we went through equilibrium, and this week we're going to go through chromatography. So there's two types. I think there's 2 types of chromatography. Yeah, there's 2 types of chromatography that we need to go through. Which is thin layer chromatography, which is the one which I think a lot of people are the most familiar with when they think of. How are you doing? Hello, Ace. I'm doing well. How are you doing today, Ace? How are you doing? But yeah, Wednesday exam. I have paper 2 for chemistry tomorrow. You're not too bad. That's pretty good. But yeah, I have paper 2 for chemistry tomorrow in the afternoon. Why, thank you. Okay, so yeah, I think thin layer chromatography is the one that most people think of when we're talking about chromatography. And I'm gonna pull up webcam like a little bit more down. I've still got a cough, so So basically, it's pretty hard to explain without like a diagram. But basically, um, you have a thin of paper, a thin of chromatography paper, and you draw like a pencil line towards the bottom of it, like not like directly at the bottom, like maybe like a little bit, like maybe like a centimeter above like the bottom of the paper, and then you would put your different like ink like mixtures onto the like either onto or slightly above the pencil line, and then what you'll do is you'll get a beaker and put a bit of solvent into it, and make sure the solvent goes up to just below the pencil line, and then when the solvent moves up the paper, it also causes the like mixture of like ink and the mixture of pigments to separate out, and then when the solvent stops like towards the top of the paper, you would put another pencil line there, and then yeah, just I think that's it for like, I mean it's the equation as well. The reason you would use a pencil line instead of just using like putting a line in pen is because pencil doesn't usually like smudge in like the whatever solvent you would use. So yeah, it doesn't smudge, so it won't like go up the page, so you know exactly like where you started from. There is an equation to work out the RF value. Do I know what RF means? I don't remember. How do you normally revise? I've been making flashcards, but feel like I need to do more. The way I usually revise is either I'll go back through PowerPoints and like remake notes, or I'll do like exam questions. Like for example, I don't know how it's like for you, but at my college we get given like question packs for like each topic, past papers. I don't do past papers. I think I've done like maybe one past paper like ever, but I feel like past papers would be good. We just get question packs, and then we can just do them like whenever. Like let me try and find when I was doing some earlier actually, and they have my college name on it. That's not good. So like for example in like here we've got, this is an organic synthesis like a question we would get, and yeah, this is the one that's on like organic synthesis and stuff. That's like the first one I just pulled out. It's not, I actually don't know where, I don't think we got, and I dropped it. I don't actually think we got one for chromatography just because it's like not that big of a topic. The only reason I'm going through it now is because I just haven't revised over it, and I haven't revised over like I know thin paper chromatography pretty well. I'm not quite confident on gas chromatography, so yeah. Okay, so the RF value, how to work this out is distance traveled by like the ink slash pigment, and this is can I insert equation? can insert, yeah, I can insert equation. So this is distance traveled by the, can I not use the travel, that is tiny, by the pigment / ink over the distance traveled by solvent. The solvent. Okay, that is tiny. Okay. What even is RFRU? I don't think it really says in this booklet. Oh yeah, and also try and give it to like at least 2 significant figures. That's what it says in the booklet anyways. So at least 2 significant figures. Okay. So it's talking about attraction between like molecules in this next bit. Completely forgot about this. So the attraction between the molecules and the solid layer is called absorption. A strong absorption means the molecule will move slowly up the plate, up like the paper, so it won't travel very far and will have a small RF value. How far the molecule can move varies, like depends on the solid coating on the like plate on the chromatography paper, the solvent used. If a compound is more soluble in a certain solvent, it will have a higher RF value in that solvent. And then there's temperature. Small changes in the setup will change the RF value. So you must run a pure sample of a known substance alongside the unknown to be able to compare it to the RF value. So, attraction between molecules equals the absorption. A strong absorption, this is just me trying to spell things, means that the molecule will move slowly up the paper / plate. So it won't travel very far and will have a small RF value. Okay, so distance traveled will depend on solid coating on the TLC plate, the solvent used. So if a molecule or compound is more soluble in a specific, what can I spell? Specific solvent, then the molecule will have a higher RF value because it will travel further. And then there's temperature. I don't know the explanation behind this, but I doubt that like this will come up as like a long like answer question. I doubt it'll come up as like a 6 marker or something. Honestly, it'll probably come up as like max 3 marker for like the factors affecting like distance traveled by the like compound, by the like molecules, by like the pigments, you know. Small changes in setup will cause our value to change. So a pure value of a known substance is used to compare. Compare like against or like alongside with the unknown value. I think I want to what am I to now? Okay, I think I want to gas chromatography now. Yeah. So probably this won't take long at all. So we'll probably be able to go through acids and bases as well as this. So gas chromatography. So a sample is injected into a stream of gas, which is carried through a tube coated with oil. Okay, so this is kind of the setup you would need for gas chromatography. So that is the like swirly bit there is like the column. We've got the syringe like here. That's like just below the syringe there is the injector port. That is the carrier gas right there, and then we've got the detector right there. The components of the gas dissolve in oil and then evaporate back into gas, redissolve in the oil, re-evaporate, etc., etc. Then substances. Oh yeah, and then the bit where the column is in, that's called the oven. Substances can then be identified based on how long they take to reach the detector, which is called the retention time. And then retention time can depend on the solubility of the compounds in the oil. So a higher solubility means the compound spends more time dissolved and will move through the like column. We'll move through the column slower. The boiling point of the compound, a low boiling point means the compound evaporates more easily and so moves through the column faster. The temperature of the like oven of the chromatography. I don't even know what the whole thing is called. The gas chromatography equipment. So the temperature of the equipment. A higher temperature means the substances will spend more time evaporating, so we'll move through the equipment faster. Okay, so let's put this into words. So gas chromatography. I don't remember doing this as a practical. I remember I've done paper chromatography as a practical like experiment beforehand, but I haven't done gas chromatography yet. I haven't done we don't have any experiments left, but yeah, we haven't done gas chromatography. I assume that this is different from between colleges, because maybe some colleges do gas chromatography. Maybe some don't. Mine didn't. Mine doesn't. So, okay, let's write this up into notes. Sample injected into the column, which is just like the column is like the stream of gas. If you saw how it was like connected, the carrier gas, the bit where the gas is in, connects to the column, so the gas will go into the column. Into the stream of stream of gas which is carried through the column which is covered in oil. And then the components are like the molecules in the gas dissolve in oil, evaporate back into gas, and dissolve again and then re-evaporate, etc., etc. And then we've got retention time, which, like I said earlier, is the time taken for the substances in the gas to be identified. Okay, time taken for the substances to reach the detector and be identified. Factors that affect retention time. So we've got 11 factors of retention time. So we've got solubility of compounds in the oil. So high solubility means that compounds spend more time dissolved and will move through will move slower. Will take longer time. So will take more longer to reach the detector. Boiling point of the compounds. So the lower the boiling point, the compound will evaporate more easily. So lower the boiling point, the higher the chance of evaporation, or it take the compound, the less time it takes for the compound to evaporate. Takes less time to reach the detector. Temperature of the gas chromatography of the equipment, I guess. I'm just gonna put environment actually. Temperature of the environment. A higher temperature means that the substances spend more time evaporated, which means they take less time to reach the detector. Let's see. Also, if you ever get some sort of a graph, kind of like this one here, the kind of spikes, just know that the area under each peak is proportional to the relative amount of each substance. So if one of the peaks is a higher area, that just means there's a higher relative amount of that substance compared to the other substances. If you don't know the concentration or amount of any of the substances in the mixture, then an external calibration curve can be used to calculate concentration from peak area So you would create a set of standard solutions of different concentrations for one of the compounds that you're analyzing. Inject each standard solution in the gas chromatographer one by one. Measure the area of the peak for each standard solution, and then plot a graph of area versus concentration, which is your calibration curve. So if concentration slash amount is unknown, then you would create calibration curve. So you would create standard solutions at different concentrations of one compound that is being analyzed. Inject each standard solution into the let's just put there's the equipment for now. Into the equipment one by one. Measure area of a peak for like each solution, and then graph of area versus concentration. Yeah, which is your calibration curve. This just means that, so basically area versus concentration just basically means area on the y-axis and concentration on the x-axis. Okay. That is pretty much all chromatography done in half an hour. So let's go through indicators for acids, bases, and buffers. If we get time, I don't know if we will or not. I might go through some more bits of like I might go through buffers for the acids and bases and buffers topic. But for now, let's just try and get acids, bases, indicators done, because I haven't really like in-depthly gone through indicators, and this is a thick booklet, so yeah. Okay, so where is indicators? Okay. So let's put a subheading of indicators. Let's see. So a little bit of background in indicators. We just talked about like pH curves and like pH meters, and Ollie Ryan Sound has finally posted his Empire Season 2 ending, and not like 3 months late. Like literally, I think Lizzie's was posted like a month ago, and I think she was like the last one other than Ollie to post like an ending to Empire Season 2. So I'm going to watch that later. I mean, depends how long it is, but yeah. So pH curves carried out with the same setup as a titration, but it uses a pH meter instead of like an indicator. So it doesn't use like phenolphthalein or methyl orange or methyl blue or anything like that. It uses pH meters. So a pH meter is used to measure the pH of a solution in a conical flask before the addition of the burette solution. Measures pH of solution in conical flask before, that's flash not flask, before addition of burette solution. And then a small portion of the burette solution is added and the pH meter is used again. So a pH meter is more precise than indicators because it can give you like the specific pH instead of like the general one, and we'll usually have put the pH as like he'll give you the specific number and he'll put it to like two decimal places. So for example, it'll say like 7.62 instead of like a pH of what is 7, like green. So but if they aren't calibrated properly, they may be less precise. Okay, so an indicator, we're gonna go back to indicators. It's used to determine the equivalence point in a titration, which is where neutralization occurs. So the equivalence point is the point in a titration at which the volume of one solution has reacted exactly with the volume of the second solution. So where the volume of one solution has reacted exactly with the volume of the second solution. For example, if there was like 1 centimeter of if there was 1 centimeter of hydrochloric acid and then 1 centimeter, let me start again. If there was 1 centimeter of hydrochloric acid and 2 centimeters of sodium hydroxide, I don't know if they react or not. I do not remember. I do not care right now. So if they get to a point where HCl has fully reacted and 1 centimeter of 1 centimeter cubed of sodium hydroxide is reacted, then that would be the equivalence point. As this is where neutralization has occurred. Okay. So indicators change color, and will have a different color based on whether the solution is acidic or alkaline/basic. I think this is pretty obvious if you have like studied chemistry and have like actually used indicators before. For example, with methyl orange, for the acidic like reactant, it would be red, and for the conjugate base, it would be yellow. And then the equivalence point, so where the concentration of the acid and the concentration of the base are like have reacted. Well, not concentration. The volume of the acid and the volume of the base has reacted exactly. Then the indicator will give off a orange color. Obviously, this is different for different indicators. So, for example, phenolphthalein will not, or like methyl blue will not show the same colors as like methyl orange, for example. Okay, so the endpoint of an indicator is the pH at which there are equal concentrations of the weak acid and its conjugate base. So, endpoint. pH where there are equal concentrations of the weak acid and its conjugate base. Okay, so the conjugate base just mean the conjugate base, like acid stuff, just basically means that in a reaction, the acid will become the base, and the base will become the acid. So, for example, H2O will become like. I'm not an example actually. I think it's in this booklet. Conjugate acids, bases. I think it is, anyways. Where is it? So, for example, let's see. Okay. Where is it? Where is conjugate? There it is. So, for example, HCl is an acid, and then its conjugate base will be a Cl minus ion, and vice versa. And like, so HCl will become Cl minus, and Cl minus will become HCl. So, let's see what else was this. Okay, well, on to the like pH curves and like some other like bits of indicators. So the endpoint of the indicator must coincide with the equivalence points of the titration. So endpoint of indicator must coincide. So like the endpoint of the indicator must fit into the range of the equivalence point. Okay, so an indicator, you've probably kind of guessed this by now, but an indicator must give a quick color change with pH, and so must change color over a small range of pHs, so that the equivalence point of the titration can be determined accurately. Let's see. So there are some pH curves that I will like show you. Let me switch to this screen, not that screen, not that screen, this screen. So just making sure these don't have my colors in them. So for example, this pH curve, and it shows this is the pH curve of a strong acid and a strong base. So at the bottom there, it is the volume of whatever base is added against pH. So pH is on the y-axis and volume of the base is on the x-axis. Did I hit something? Did I accidentally reload stream? Oh no, I don't think I did. I'm moving my keyboard away right now so I don't accidentally reload stream. This is the reason I can't have hotkeys. I remember once a while ago, I can't remember what it was, but basically a while ago when was it? It was a while ago, but basically, I remember I was streaming and my and Be Real went off, and this was at the time of when like okay, I don't remember when it was. I think it was Friday 10th of March, maybe, I don't know. But basically, I remember, so this is at a time when I'll do like, this is like the little bit of time when I'll do my Instagram live streams as well as my Twitch live streams. And so I had my things up. I had my tripod set up like right next to, like here where I've got like right, like in the space between my monitor and my mic, right. And the reel went off, so I went to get my phone off the tripod and, you know, take the reel. The tripod fell into my keyboard and restarted stream. So yeah. So this is the pH curve of a strong acid and a weak base. So you can see this top like part of the curve here is at a is like shorter, as is at like a lower pH, ends at like a lower pH than the strong acid, strong base curve. And then we've got the weak acid, strong base curve. So as you can see, this part here, this starts higher at a higher pH than the ones with a strong acid. You can kind of see a trend now. But yeah, we've also got weak acid, weak base. So this ends at a lower pH and starts at a higher pH. So you can see kind of there's a very low, like basically non-existent equivalence point there. Like it's still there. Like I think the general acceptance of like what the equivalence point is for a weak acid, a weak base pH curve would be like 6 to 8, would be like 6 to 8 on the pH scale. While for example for strong acid, strong base, it's like, I think it's like 2 to 10 or like 4 to 10. I don't remember, and I don't think you have to like remember, but I'm not sure. Just like, I think you just kind of get, I think it's 2 to 10 actually. I think it is 2 to 10. I think that's it. That's it for indicators. I think I might go over something else. Let me switch back to this screen right here. What else? Okay, I think we'll go through some basic definitions from this topic. So, from like the acids, bases, buffers solution topic as a whole. So, the general accepted. Okay, so the Bronsted-Lowry acid definition. So Bronsted-Lowry acid definition just basically means it's a proton slash H plus donut. And then if you're wondering, wait, a proton and H plus the same thing? Yes, because if you go back to like when you first like were talking about the periodic table, you kind of might have talked about this, but basically a hydrogen atom is just a proton and an electron. So for example, if you had an H minus ion, that would just be the electron because you've taken the proton away, and for H plus you've taken the electron away. Oh wait, no, for H minus you've added an electron. You can't really take protons away. Not to my knowledge. Not to my knowledge, at least. But yeah. So with H plus, you've taken away that one electron, so it's literally just the proton now because there's no like neutrons. So you might guess this, but a base is defined as a proton slash H plus acceptor. And then the definition of an acid-base reaction, well, that's just the transfer of a proton slash transfer of H plus. Okay, so let's see. Okay, so monobasic, dibasic, and tribasic acids. So a monobasic acid just releases. So a monobasic acid, when it dissociates in water, it releases one proton, one H plus. And you can usually tell this by the equation, for example, by like the molecule itself. So for example, HCl only has one H in it, so that's monobasic, and it will only release one H plus ion. H2SO4, okay, I'm going to get on to dibasic. H2SO4 would not be monobasic because it has two H plus. Okay, so and H2SO4 would be example of a dibasic acid, which means that when dissociating in water, it releases two protons slash H plus. So for example, H2SO4 will release two H plus. And then there's a tribasic acid. When it dissociates in water, it releases three protons. And I don't think we don't really need to know about like anything beyond that. So for example, phosphoric acid, aka H3PO4, that will release three hydrogens. It will release three H plus. Okay, so a salt. This basically means this basically means that a salt is a compound produced when one H plus ion from an acid is replaced by a metal or another positive ion, such as the quaternary ammonium ion, so NH4 plus, or it's replaced by like sodium or magnesium. So a salt is produced when a H plus ion is replaced. Okay, so H plus ion from an acid is replaced by a metal or another positive ion, e.g. NH4 plus or Na plus or Mg2 plus. So yeah. Let's see what else. Okay, conjugate acid base pair. Conjugate acid base pair. This is where a pair of two species transform into each other by the gain or loss of a proton. So, two species fall into each other via the gain or loss of a proton / H plus. So an acid would become a base by removing H plus, and then a base would become an acid by gaining H plus. So for example, HCl, an acid, would become Cl by would become Cl minus by removing H plus. Also be careful, because for example, HCl, like the acids, so like HCl, H2SO4, might not be a conjugate acid. You will have to actually look at the pairs and whether H plus has been lost or gained. Because for example, in an equation, like if you've given an equation, it could be like HCl into like H2Cl2, you know, or it could be like H2Cl, you know, like H2Cl plus. That would be the thing. But yeah, so okay, strong acids versus weak acids. So a strong acid fully dissociates in a solution, such as water, and during this dissociation, during dissociation, equilibrium moves far to the right, so the reverse reaction is not significant, and it's a complete dissociation. So it doesn't just like undissociate. It doesn't then, like, for example, become like HCl again. It will stay like H plus and Cl minus, and the concentration of H plus is high. So there's a high concentration. High concentration of H plus. So let me put strong acid there. Strong acid. And then there's weak acids, which partially dissociates in a solution, such as like water. So during dissociation, now this one you can kind of already guess from what we discussed. It's just like kind of the opposite of what we started out for strong acids. So for a weak acid, equilibrium equilibrium moves far to the left. The reverse reaction is, okay, I spelled that wrong. First reaction is significant. Dissociation is partial, so it's an incomplete dissociation. Low concentration of H plus compared to the undissociated, compared to like the concentration of the undissociated acid, compared to concentration of undissociated acid. Okay, I think that's all I'm really gonna go through for Today, we're just gonna ramble on for the next 10 minutes. Not 10 minutes, 5 minutes before I end stream. Yeah, I hope you have enjoyed this stream. I'm just looking at my head. But yeah, since I finish my A levels next week, there'll be no more revision streams. No more A level revision streams, at least. I might do some when I get to uni. I don't know. Maybe I will. Maybe I won't. I know a lot of people like on TikTok do like study streams or like revision streams. So maybe I'll do one like over here. So since I won't be doing a revision stream next week, I do have an idea of what to do. I have like two ideas. Either inside the back rooms or Hermitcraft GeoGuessr. You know, you wanna hey guys, you wanna do a round of Hermitcraft GeoGuessr like right now? Because I've been kind of obsessed with it. Basically, Green posted a video onto his second YouTube channel. It was him and Star playing Hermitcraft GeoGuessr, and I really want to play just like one round of it, and then see like how you guys like feel about it. So let's open that up. That should be okay. Yeah. Fucking tell. Okay, so you can choose seasons from 4. You can choose seasons 4, 5, 6, 7, and 8. The background here is season 8. I have only watched season 8, and I'm only somewhat familiar with season 7, so we're gonna stick to season 8. We got 5 rounds of this. 5 rounds of this. Oh, this is bottom. Okay, we're in Mumbo's place. We're in Mumbo's. Which part of Mumbo's? We're in the. There's a bit below us, so. We're about. I'm on Birch. So we're somewhere here on Mumbo's base. There's one bridge above us, which makes me think that we're not on one of those bridges though. So I'm going. Oh, we're here. We're literally here. And we're literally there. One block off. Okay. Oh, I've gotten this one quite a few times, and I do not know where it is. This is a problem with me only watching Korean for like the whole of season 7. Okay. This looks like plains grass. It's plains grass. I have no idea where it could be, so let's take a wild guess and go for like, I don't even know where it would be. That's a swamp, and then I'm just gonna go for like that. I know that's not the right answer though. Okay, what about 1,000, 5,000? Oh, there it is. Okay. Okay. So the top is spruce. I have a feeling of where this might be. Oh god. Again, this is what happens when I only watch Korean. Hopefully, if whoever makes this, oh god, hopefully whoever makes this will update to, oh god, I've seen this part before, but where is it? Here? Somewhere? Okay, no, I'm over 1,000 blocks away. Oh god. Okay, we're somewhere in the mesa, so it's literally just the dripstone, but where specifically? Oh god. Okay, we need like, there's somewhere in here. We need like a are we here? I can't tell. Oh wait, we're here. We're near here. We're near here. So we're like roughly. Okay, we would be roughly about here. I want to say here. Oh, we're on the other side. Okay, we have one more, I think. Oh god, I've done this one before as well. You can tell I'm not great at this. Okay, we're in mountains, which isn't great for this. So, okay, dark oakwood forest. That's a sugarcane farm. Oh wait, I think I've seen this. Are we like around here? We're on an obsidian block. I think it's here. Where's the obsidian block though? Am I just blind? Oh, yeah, it's somewhere around here. Because you can see it's the crisscross of the course there and the mossy cobble. Unless there's another one. Oh yeah, yeah, we are here. We are here. So, like, there, I want to say there. 2 blocks away. Okay. So, yeah, I'm gonna go. I'm gonna end stream here. I hope you have enjoyed. I'm gonna go to Twitch real quick to see if there's anybody to raid, but if not, I'll keep it open. No, there's no one I want to raid. I hope you have enjoyed the stream, and I shall see you next week. I shall see you next week on Friday for the Lego Ninja